Hi there, welcome to this video. This is 9-1. We're talking exponential modeling in context. I am here live with the class, so if you hear any hoodlums in the background, that is them. All right, so let's go ahead and get to it. Our objective, we want to use exponential models to solve context problems. All right, prior knowledge. Go ahead and pause the video and try this. It says here the number of bacteria in a petri dish can be modeled by the function b of t, which is equal to 50 times 4 to the power of t, where t is in hours. So quick question, how many bacteria will there be when t is equal to 1/2? Pause the video and give this a go. Alrighty, so in order to find out how many bacteria there will be when t is equal to 1/2, all we do is we evaluate the function at 1/2. So b of 1/2. This is equal to 50 times 4 to the power of 1/2. Now, really the prior knowledge that we should have remembered from our radicals unit is that a power 1/2 is the same thing as a square root. This is 50 times the square root of 4. So what's the square root of 4? Very good. 50 times 2 is 100. So in 1/2 hour, after 30 minutes, there's going to be 100 bacteria. 100 bacteria. Alrighty, so here is the concept for this lesson. We're going to talk about exponential models, and there's two types of exponential functions that we look at or consider. There's exponential growth, which here is a visual of what exponential growth looks like. This can be modeled something like a TikTok video going viral. Or, hey, what do you know, maybe a disease, something like COVID, spreading, how it will spread exponentially from person to person. Okay, so this is exponential growth. That's when something multiplies or gets bigger and bigger. The next type is called exponential decay. Now, exponential decay has a value that decreases, and an application of this would be like radioactive material that decays, or an application for crime scene investigators determining when a body is, when it died, based upon the amount of decay. So those are some applications of exponential growth and decay. What we want to go ahead and focus on is the formula here. If I have an exponential growth function, the formula is f of t is equal to a times 1 plus r to the power of t. A is your initial value, and a must be greater than 0. Another application of this can be interest. So if you're going to invest money, a would be the initial amount of money you put forth to invest. R, this is the constant percent increase, your growth rate. And this, in this case, if you're talking about interest, it would be your interest return. So if you're getting an 8% return, you would add 0.08. It's expressed as a decimal, and I'll put this as an example. So 8% is 0.08. Okay, and t is time. Exponential decay is extremely similar. F of t is equal to a times 1 minus r to the power of t. Here we have an a value still. I still have an initial value that's a, but r in this case is decrease. We're subtracting that rate, okay? And we'll go ahead and look over some of these examples here in a second. All right, so let's go ahead and put this into application. Here's our first example. And in this example, I'm going to go ahead and annotate. So especially when you have a context problem, highlight or write down the key information that's given. It says here, Tony purchased a rare guitar in 2000 for $12,000. Experts estimate that its value will increase by 14% per year. It's increasing. So right away, you know that it's increasing. This should be exponential growth. And they tell us that here in part A. It says write a function using the model v of t is equal to a times 1 plus r to the power of t to find the value of the guitar t years after it was purchased. Okay, so let's look at the information that they gave us. Tony, he purchased it for $12,000. That's his initial investment. A is $12,000. His rate, the R value, is 14%. That's how much it's going to increase each year. And this has to be entered as a decimal. So what we're going to do is we're going to go ahead and divide by 100. So 14 divided by 100, 0.14. The quickest way for me to think about this is I just think about it in change. Like 100% is $1. So 14% is just 14 cents. So 0.14. That's kind of how my mind interprets this. Okay, so I have these values. Now I'm going to go ahead and I'm going to use this model. So V of t, the value of the guitar based upon time, is equal to $12,000, 1, 2, 3, times 1 plus r. So 1 plus 0.14 to the power of t. Yes, we're going to go ahead and simplify that exponential base. That's really, really simple. So add it together. 1.14 to the power of t. There is your exponential model. All right, so now let's go ahead and find out how much the guitar will be worth in 2009. So avoid the pitfall here. You need to identify what value of t you're going to plug into your function. T is not 2009. We need to figure out t is the years after it was purchased. So Tony purchased it here in 2000. So I'm just going to go ahead and do some simple subtraction. 2009 subtract 2000. So this is 9. So our t value that we plug into the function is going to be 9. Okay, so now I just take my function, v of t, so v evaluated at 9. So this is 12,000 multiplied times 1.14 to the power of 9. Here's where you're going to want to utilize a calculator. Now you can go to desmos.com and use their scientific calculator. That's a good one. Or you can use the TI Inspire if you're here in class, which looks just like this. And I'm going to teach you how to input exponents if you don't remember or know how to do so already. The exponent button, if you're not using power 2, because here's power of 2, it's this caret button. So if you want to go ahead and type in an exponent, I'll show you here what it looks like on our calculator. So we're going to enter 12,000, 1, 2, 3, 12,000, multiply. I'm going to go ahead and hit the multiplication button. And I'm going to multiply by the base, so 1.14. And then I'm going to enter a caret. So that's this button right here, little up arrow. And then I enter my exponent, so to the power of 9. So we go ahead and enter that, and that will be our answer, if I can find my place here. Okay, so this is approximately, okay, so this would be $39,000, $23.38. Man, in 10 years, essentially 10 years, that's a good investment, I would say. Good investment, okay? This is a word problem, so we do want to respond in a sentence. So we say, in 2009, the guitar was worth $39,023.38. Okay. All right, here is the second example. In example number 2, they say a certain stock opens on the market at a value of $29.32. Over the 4 days, the value of the stock increases at a rate of 5.5% per day. So question A, write a function to model the value of the stock using the function S of D is equal to A times 1 plus R to the power of D. So our A value, the stock was initially worth or bought at $29.32 a share. The rate, they say, is 5.5%. So expressed as a decimal, this is 5, so 0.055. Okay, again, if you want to find that value, you can go ahead and divide by 100, or you can think about 5%. That's going to be a nickel, right? 0.05, and then another 5. So there's our rate. Okay, so let's go ahead and write our function. Bless you. So S, the stock, based upon the day, and again, this model is only good for 4 days. So S of D is equal to A, so I have 29.32 times 1 plus 0.055 to the power of D. And again, we'll go ahead and simplify this. So 29.32 times 1.055 to the power of D. Okay. All right, so there is the function. Part B. It says if this trend continues, so if it continues over the next week or more, over the 4 days, how much will the stock be worth 1 week later? Okay, so again, we need to find, in this case, D. D is equal to, so 1 week. Notice D is in days, so 1 week, this is the same thing as 7 days. We're going to assume that this stock trades on the weekends. Okay, so 7 days. All right, so then we're going to go ahead and evaluate. So S of 7, so 29.32 times 1.055 to the power of 7. Okay, so we'll go ahead and plug that into our calculator. And we get approximately 42.65. So 1 week later, the stock will be worth about $42.65 a share. All right, there we go. All right, here is an example. Please go ahead, pause the video, write a function for the given context, and then answer part B, how much will the baseball card be worth in 40 years? I'll appear here in a second. I'll talk about the function before you can go ahead and try part B. So please pause the video, write the function. All right, I'm going to go ahead and go over the A value and the R value that is used in order to complete this function. The card was initially purchased for $3.25. So that's your initial value, your A value. The rate is 11% per year. Wow, that's a really good return on investment. So 0.11 is your R value. Okay, so our function, if that's our A and our R, is going to be V of t is equal to 3.25. So we take our initial value, multiply by 1 plus R, so 1.11. Make sure you add that. Don't be lazy and just leave it as 1 plus 0.11 to the power of t. So there's your function, okay? If you have not already, go ahead, pause the video, and plug in, evaluate how much will this card be worth in 40 years. All right, so hopefully you went ahead and evaluated. Here are the solutions. So after 40 years, dang, this baseball card's gonna be worth $211. Maybe you're like, hey, $200, that's not that much. Well, he bought it for $3. That's a heck of an investment. Okay. All right. Next example. All right, the last couple of examples have been exponential growth. We're now going to go ahead and look at an exponential decay example. And here we have a value of a truck purchased for new for $28,000, depreciates by 9.5% each year. They say write a function for this situation using the model v of t is equal to a times 1 minus r. Remember, if we have exponential decay, we need to subtract that rate. So this truck's losing value. So purchase new for $28,000. That's the A value. Our R value, the rate, it's depreciating at 9.5%. So we'll convert that to a decimal. So 9% and a half. So 0.095. Okay, so our model is going to be v of t is equal to a, that's 28,000, times 1 minus the rate, minus 0.095 to the power of t. Okay, and we'll go ahead and simplify. So if you need to, you can use your calculator or you can use mental math. So our base of the exponential model is 0.905 to the power of t. Okay, so that is our function. Part B, it says estimate how much the truck will be worth 12 years after purchase. In this example and in the last practice problem, they just gave us t straight up. They say after 12 years, and 12 years have passed. How long? So we don't have to do any roundabout ways of finding what 12 is. So I'm going to evaluate what is v of 12. 12 years later, 28,000 times 0.905 to the power of 12. Okay. It's sad, really, how fast cars lose their value. It's like $10,000 right when you drive off the lot. Something wild like that. Okay, and I got $8,451.64. Okay, so in 12 years, the truck will be worth about $8,451.64. All right, here is the next practice problem. They say on federal income tax returns, self-employed people can depreciate the value of business equipment. Suppose a computer valued at $2,765 depreciates at a rate of 30% per year. Go ahead, pause the video, write a function for the situation, and then evaluate in part B the value of the computer in 5 years. Alrighty, hopefully you had a chance to try this practice problem. Here is our function model. The initial value of the computer was $2,765. The rate is 30%, and again, that's depreciation. So the base, you're going to subtract that from 1. The computer only retains 70% of its value each year. So there's our function, v of t equals 2,765 times 0.7 to the power of t. And then we want to evaluate what is the value of the computer in 5 years. So if we evaluate at 5, we get approximately $464.71. Okay, before you go, here is a closure. And it says determine whether the following examples are exponential growth or exponential decay, and then circle the response. Go ahead and pause the video, try that really quickly. All right, hopefully you went ahead and were able to look at these two functions and determine which one's growth and decay. The base is what tells you which one's growth and decay. So if you look on the left side, 0.92, that's decay, and on the right side, that's exponential growth. All right, hope you learned how to go ahead, model and compute exponential growth models. I'll catch you in the next video. Peace.